Why is this not the default way? Because we're the first ones to do it.
The thing that I want to understand most is how damage initiates.
My work is focused a lot in the area of composite materials, specifically composites that we denote as multifunctional composites.
And my goal is to understand what happens to the material just before damage initiates. I call it precursor, because if I can understand that the current composite, high-performance composites are behaving in a certain way through predictive models, then I can actually design materials with better properties so that the crack doesn't initiate.
We recently, and by recently I mean within the last year, we acquired a new equipment called a micro load frame. Composites are very complex. Because of this complexity, there's equally amounts of complexity in how they fail. Having this novel system, our goal then is can we capture that behavior directly? Can we see it?
You can't replace experiments, but you can minimize the number of experiments. So we developed a model which for the first time actually bridging molecular dynamics to continuum scale. Continuum scale meaning actual materials, not at the atomistic scale. But if you can understand how things happen at that scale where things are initiating and bring that knowledge to the continuum scale, then you're really looking at tracking damage from the inception.
The biggest problem scientifically we are working on right now is basically developing effective conductors, electrical conductors specifically, that is way better than conventional metal-based conductors. So when you add something to metal conductor, it gets worse in terms of electrical conductivity. So instead of mixing atoms in order to develop new conductors, our approach is basically composite. We have a copper wire and then synthesize high quality continuous graphene on top of copper wires so that we can actually truly integrate the advantages from both. So the best performance we have achieved using this approach is about 20% above baseline, basically only the copper wires, which is the highest recorded in the entire literature at this point. So we are very proud of this work. I would like to introduce my PhD student who has been working on different types of graphene-coated copper structures.
This is our homemade CVD system. CVD is the abbreviation of chemical vapor deposition. So that's the technique we use to grow or deposit graphene on the surface of the copper substrate. I think it has been about 1 year, so I can do the research kind of independently, but still now I need the supervision from my professor.
As a PI, I can rely on her research approaches, experimental data, as well as her analysis section. So that's my ultimate goal. Someone become independent and reliable, eventually colleagues, right?
Yes, yes.
So I just received $50,000 as a part of the SkySong Startup Challenge. I was pitching our layerless 3D printing method, and that won the grand prize of $50,000. Metal printing right now, it consists of using lasers and very high temperature equipment that's just so costly. It costs you hundreds of thousands of dollars just to have one metal printer. We do a volumetric approach where we just continually ascend our build platform to form the part in minutes. We 3D print the digital model to the shape that we want, and then we take this printed part and then we post-process it with furnaces to convert this metal precursor into a pure metal part. So something like this is a copper piece, and so you can't machine something like this, or you can't do metal injection molding to make something like this. Why is this not the default way? Because we're the first ones to do it. This is not just for research. We're not just doing this for fun. We want to make the world a better place and commercialize this and put this out so that people can make more interesting parts and have more design freedom in their choices when they're engineering things.